Good morning. Welcome to day 2 of the ELAP Conference. I'm Catlin Bloom, Conference Co-Chair, and we are so excited to have all of you joining us and for you to hear from all of our great presenters today. We have just a few housekeeping things before we move on. You will notice that this platform is different than others you may have used. As an attendee, you can unmute yourself or turn your camera. You can't unmute yourself or turn your camera on. Sorry. Any questions you wish to pose to our presenters can be done through the Q&A chat box. We encourage you to put your name in the space provided so that we know who you are. On your screen, you should see how to submit your questions via chat. And during today's event, feel free to send in your questions through their presentations, and we'll pose all the questions to the presenters after the presentations. If you're having any technical difficulties with the event, we recommend that you leave the event and come back, and that should resolve your issue. Don't worry about missing anything. We'll be posting a recording on each day of the California ELAP YouTube channel for you to view at your convenience. And if you have any friends or coworkers who are unable to join us today, this is a great way for them to view the conference later. We also encourage you to join the fun on the ELAP Conference Slack channel. And there's a link to that in the chat for you right now. So feel free to stop in, say hello, meet some colleagues, and ask your questions. It is our hope that we can capture a small part of the social aspect of a conference in a virtual setting. You'll even see some of our presenters there, and I'm sure that they would be happy to answer questions, just like if you saw them in the hallway at a conference. ELAP members will be stopping in and chatting, but if you have specific questions, it's still best to send an email to our general inbox. Now I'm going to welcome my other half, Jen, to give us an overview of today and introduce our keynote speaker.
Thank you so much, Kat. We are looking forward to another great day here at ELAPCon. Thank you for being such a wonderful audience. It has been great interacting with you via the chat box, email, and on our Slack channel. The more involved you are, the more everyone benefits, so thank you for your participation. Today is another day packed full of presentations. We're going to hear from Dr. Zhenyu Tian of the University of Washington talking to us about 6-ppd quinone, followed by Dr. Yegi Dearborn with a presentation about EPA 1693 and parasite detection. Dr. Charles Wong is going to give a presentation about microplastics, followed by Dr. Susanna Thoreau with a talk about eDNA. Next, we'll hear from one of our steering committee members, Charles Nesland, with a presentation about PFAS. And we'll wrap up the morning learning about ddPCR from Dr. Chad Crane. That's a lot to get through in one morning, so I won't keep you waiting. I'd like to introduce our keynote for today, Dr. Augustin Pieri. Dr. Pieri obtained his Bachelor's of Science in Chemistry from the University of Southern California and his PhD in Chemistry from the University of California, Santa Barbara, where he worked on synthesizing photoactive pharmaceuticals and nanocarriers. He has authored many scientific publications and has given numerous presentations at technical meetings on topics ranging from inorganic photochemistry to environmental analytical chemistry. At WEC Labs, he has worked as a bench chemist in all sections of the laboratory, which includes microbiology, inorganics, and organics. Additionally, he has extensive experience developing and validating methods for merging contaminants by sophisticated techniques such as LC-MS-MS, GC-MS-MS, and ICP-MS. Since becoming the laboratory technical director in 2016, he continues to be active in developing methods for novel contaminants, as well as modernizing legacy analytical methods to lower detection limits and improve data quality. On top of all that, Augustin serves as a member of the Environmental Laboratory Technical Advisory Committee and was part of the steering committee for this conference. We're so pleased to welcome Augustin to the ELAPCon stage.
Thanks, Jen, for the introduction. And I think my PowerPoint should fire up there just a minute. So yeah, thanks for the introduction, Jen, and thanks for the opportunity to speak at the very first ELAP conference. I'm really excited to be here. It's, I think, going to be a great conference, and it'll be great going forward too for the next however many years we do it. But good morning, everybody. Today I'll be talking about how the lab community in California is leading the charge to be the lab of the future. Now, before I start, I want to give a little bit of background on our lab. Slide, please. So we're a medium-sized lab with about 70 people down in Southern California. Like many other ELAP accredited labs in California, we started as a pretty small lab back in the 60s. And over the years, we've grown, and now our ELAP certificate actually has over 600 method analyte matrix combinations. So currently our scope of work, our scope of testing services kind of include a little bit of everything. We do some volatiles, some semi-volatiles, metals, microbiology, and radiochemistry. Now, over the years, we've been very involved and continue to be very involved in emerging contaminants. I think my PowerPoint's not going all the way through, but I'll try to make it work with what we got. Can I get the next slide, please? Yeah, we've been heavily involved in emerging contaminants over the years. And when I started working on this talk, I sat and thought, are we in the future now? Is this the lab of the future today? And, I don't have a flying car. I don't have a jetpack, even though people like to drive on the freeway like the cars fly. We've, in California, have always been at the forefront of environmental testing. Now, it's always looking for what's coming up and what's on the horizon and trying to stay one step ahead of that, which is kind of what I'm proud of, to be part of this community. So a good example of this is the emerging contaminants. Next slide, please. So throughout California's history, we've always been about innovation and progress. And unfortunately, all this progress inevitably led to significant contamination at former industrial sites and other contaminated areas. So fast forwarding, through the 80s and the start of the Superfund program, we now have, I think, like 100 Superfund sites across the state. And one example that kind of hit close to home for us was right here in our backyard in the San Gabriel Valley. Since those early days of environmental testing, labs like ours were continually making improvements to methods for the ultimate goal of meeting these ever-decreasing regulatory limits for these emerging contaminants at the time. And we were investing in state-of-the-art Persian trap GCMSs, and we were using them to look for things like TCE and PCE at less than 5 ppb in groundwater, which at the time was really low. We're also doing stuff like modifying our ICs to look for perchlorate and Chrome 6 in the low ppb range and even lower now. And we try to make these improvements to reach those low limits and stay ahead of these emerging contaminants and be able to provide the services that were needed from us. Over the years, we started, in addition to improving methods and lowering limits of detection, we started looking at ways to improve efficiency and do more automation and have better data quality. So we switched systems for manual injectors to auto samplers and things like that, where we could just make improvements. In our lab, the efforts didn't end there. I mean, it's not something that finished in the 80s and we don't do that anymore. The pursuit for emerging contaminants, or CCs as we call them too, constituents of emerging concern, just continue today. Slide, please. So while many regulated contaminants first started as CECs, a kind of a recent example is the analysis of PPCPs. These are pharmaceuticals and personal care products as anthropogenic markers in the environment. The type of testing only came to the forefront because of rapid improvements in analytical technology. Namely, it was the advent of the LC-MS-MS. This let us measure things that were non-volatile and not amenable to gas chromatography. So this kind of gave us the opening to look for these kind of elusive targets. And a landmark study published by USGS maybe 20 years ago now showed that some pharmaceuticals, either due to low bioavailability or improper disposal or one reason or another, make it into the wastewater streams and into the effluents and subsequently into the environment. And this is especially critical in places like California, which relies on recycled water, so it becomes a little bit more alarming. So when this became an issue, to fulfill that need, our lab, like many others in the state, developed methods for PCPs even before the EPA published their own methods, because there was that need for an emerging contaminant. Slide, please. So we've been analyzing for PCPs for something like maybe 13 or 14 years at this point. And kind of around that time, we also developed our first method for everyone's favorite emerging contaminant, PFAS. This is something so ubiquitous that there was even a Hollywood movie about it. And the movie's actually pretty good. If you guys get a chance to watch it, I recommend it. But over the years, labs in California have expanded their PFAS methods to accommodate the growing need for more information, either more targets or lower detection limits. Our first method only had 2 targets, PFOA and PFOS, at maybe 1 ppb or something. And over the years, it grew from 2 to 6, then 13, then to 18 and 28. And now we're looking at a list that's almost 50 targets at 1 nanogram per liter. Slide, please. In addition to CCs that are all over the news like PFAS, California labs also tackle other kind of important contaminants in support of very specific requests from particular regions or agencies in the state. A good example that happened just a little while ago was the Central Valley Regional Board had a request for testing for pyrethroid pesticides. So it's a very agricultural heavy area and they're worried about pesticides, but they wanted to look at these pesticides at really low levels. And not only were these pesticides not available on existing EPA methods, they didn't have methodology for these newer non-regulated pesticides, but they're also looking at or wanting to look at levels that were much lower than what current methods and technologies could handle. So in response to this need, the California lab community stepped up and answered the call by developing and validating methods to meet the needs of this particular request from the regional board. Slide, please. Also, there seems to be kind of a growing need in the same region, these agricultural regions in California, for detecting a newer class of insecticide called neonicotinoids. And these pesticides have also kind of been in the news because they were linked to a phenomenon called colony collapse disorder. And this is, it's thought that the overuse of these insecticides might have some effects. They're not fatal, they're like sublethal effects on bees. So while not killing them outright, it might affect their ability to do certain things and indirectly lead to colony collapse. And because bees are essential pollinators in agricultural production and very important to the whole process, it's pretty important to do whatever is necessary to determine what could be affecting these bees. It could be the pesticides, it could not be, but the only way to know is to do the testing. So to meet this need, several California labs have already developed methods for determining these insecticides using state-of-the-art technology like LC-MS. This is another example of a compound class that just wouldn't work by GC-MS. There was no way to detect these in the old days because they just wouldn't work with the existing technology. Slide, please. So using that kind of state-of-the-art technology is another example where California labs are just leading the charge towards being the lab of the future. The lab community is always investing in sophisticated technology like tandem mass spec, both with the GC and LC front end. The GC-MS systems are used for ultra-trace pyrethroid measurements, like I mentioned earlier, and also for things like nitrosamines, which are disinfection byproducts that really can only be measured by tandem mass spec. And right now, the biggest use for LC-MS is obviously PFAS, and we're looking for always getting lower limits and more robust methods to better handle different matrices and kind of complicated samples. Labs are also looking to implement new technologies like digital droplet PCR or microscopes for microplastics analysis, and of course more robotic automation for improving workflows in the lab. And what could be more lab of the future than robots, right? So everybody wants to have more robots in the lab. Slide, please. Oh, and also in that picture is a very rare picture of me in the lab that I don't get a chance to be in the lab anymore. Back when I had short hair and had a little more available time, I guess. So while the stuff that we talked about were just some of the examples of emerging issues that we had that the California labs have worked on, I'm really looking forward to the talks that we have today. We have a bunch of great talks on a bunch of interesting topics that I think would be, really a good example of the lab of the future and the things that California labs will be working on. Things like developing, validating methods for microplastics testing, testing and identification of that brand new contaminant that literally just emerged a few months ago called 6-PPED quinone. That's a degradation product of tire wear that kills coho salmon. Use of EDNA or molecular techniques for eDNA and Enterococcus. And of course, because PFAS is always looming, we'll be able to hear about a new EPA method for drinking water, for PFAS in drinking water. Slide, please. So let's say that one or more of these emerging topics becomes a testing need, and a state agency requests that those analytes be monitored. That request would typically go to ELAP and into a group called the Environmental Laboratory Technical Advisory Committee, LTAC, which I'm part of. So as an example, the pyrethroid request from the regional board I mentioned earlier actually came to LTAC before the request for methods went out to the labs. Slide, please. So LTAC kind of serves as a bridge that can help close the gap between research, accreditation, and monitoring. Oftentimes the contaminant of interest, say, comes out of like an academic research group, and then a need emerges to monitor in the environment. So a state agency says, we need to test for this, but before we can actually do the testing, a method has to come out, and that's up to the lab community to develop the method and validate it to make sure that it is going to be suitable for that contaminant, or whatever you're looking for. It'll work in the matrix you're looking at, and also that it meets the stringent data quality requirements for that kind of measurement. So LTAC kind of facilitates this process and gives guidance and recommendations to ELAP when making these accreditation decisions. And along those lines, LTAC is also currently working on a document which will help assess if a proposed method is fit for use. We envision that this document will be used by folks ranging from data end users to see if the data meets their criteria. It could also be useful for smaller labs who are subcontracting analyses to other labs to determine if the data meets their data quality objectives. It could be used by state agencies who would want to use this while requesting methods to see if the proposed methods would meet their end goals, meet their needs of the monitoring or measurement. It could also even be used by the labs themselves to help validate the method and kind of streamline the whole process. And at the very end of the chain, it'll help ELAP assess if a method should be available for accreditation or not. Slide, please. So none of this could be possible without collaboration within the community, and something that's kind of the theme of the whole conference. But collaboration is huge. I mean, it's huge in the lab community, it's huge in LTAC, and it's a big part of everything that we do. So LTAC is made up of people from all parts of the larger testing and regulatory community. We have folks from kind of all branches that all provide, very useful and valuable insight so that we as a group can make, the best informed decisions and recommendations to ELAP. And it really wouldn't be possible without this collaboration. I'm also personally a really big advocate for open communications within the entire lab community, something that is always useful to have open dialogue between the labs and the regulators and the accreditation folks, and have everybody kind of talking and be on the same page. That's also why I feel very honored to be part of this very first conference. It is exactly the kind of interaction within the community that'll serve to improve the work that we all do in general. And, California labs are the labs of the future, so I really don't know what the future holds, but I'm pretty excited to see where it's all going to take us. Next slide. And with that, I'll send it back to Kat. And I guess I'll be available for questions in the Q&A later.
Thank you, Augustine. That was a wonderful start to the day. Next, we would like to welcome our first presentation of the morning. Dr. Zhen Yutian is a postdoctoral research scientist at the Center in the University of Tacoma, applying non-target screening to identify emerging contaminants in stormwater, marine water regulations. He received his PhD in environmental sciences and engineering from the University of North Carolina in Chapel Hill. His research interests include emerging contaminants, suspect and non-target screening, high-resolution mass spectrometry, metabolomics, and bioremediation. Please welcome Zhen Yu.
Hello, can you hear me?
Yes.
Okay, thank you. So I'm not sure. Hello, everyone. Good morning. It's my pleasure to present some of our research to you. I'm not sure which version of this, but I have some small difficulties with the slide. Hopefully we can get this through. Okay. Is this the most updated one? Can we check it through a little bit? Awesome, great. Okay, yeah, the video is going, cool. Let's start, thank you. Next slide, please. So the topic is about 6-ppdquinone, which is the salmon toxicant that we recently identified. So first, I'd like to thank my collaborators and colleagues. So this is really collaborated work. We have local, national, and international collaborators, and especially this meeting is about California. So we can see a lot of California, not a lot, major like 2 California collaborators, SFEI and SCWRP. So these are really, I'd like to thank everyone for their contribution. Next slide, please. So this story begins with a phenomenon called urban runoff mortality syndrome. It happens in the greater Seattle area, and especially to a larger degree Pacific Northwest every year after the fall storms, usually in late October to November, when the coho salmon are swimming up the creeks to lay their eggs. In some urbanized areas, we see the coho salmon were showing some weird symptoms, like losing equilibrium, gaping for air, and swimming in circles. We can play the video here, I believe, or not. Okay. Yep. Here we go. Okay, still some issues. That's fine. So generally, we will see the maybe later video about that. And once they show the symptom, they will be dead just in a few hours, so pretty fast. And this phenomenon is also specific to coho salmon, but not other salmon species like chum salmon, although they are living in the same urbanized creeks. So this is pretty like a prevalent phenomenon in the greater Seattle area. And if this trend continues, we can see this B panel that the coho salmon in this area will die out just in several decades. So it's a big problem. Next slide, please. And our collaborators in NOAA and WSU, they have been investigating this for a few years. And their observation is that it's related to urbanization gradient, especially the traffic intensities. So we can see the left map in the red areas, those are where coho mortality risk are the highest, and those are also the traffic intensities are pretty high. So this agreed very well. It's a prediction model. And because of such observation, the collaborators, they collected runoff from busy highways such as the SR 520 bridge in Seattle, and they exposed the coho salmon to this runoff. And they found that coho salmon were killed pretty fast, and they're showing the same symptom as observed in the creeks. So the preliminary conclusion is that this toxicant for this phenomenon is probably related to road or cars, although it's unknown to them at that moment. Next slide, please. Okay, so when our group came into this collaboration, we used a high-resolution mass spectrometer to profile the chemistry of different water samples. And we know like the runoff kills coho mortality, and we also have some samples collected from the mortality event in the creeks, right? So we can see all this red highlighted samples, those are the samples that related to coho mortality. And we also have some vehicle-related sources like windshield wiper fluid, motor oil, and antifreeze. So we compare their profile with high-resolution mass spectrometer and use this cluster analysis to see which one is similar to the toxic field water samples. And turn out that tire wear particle leachate seems very similar with the runoff and the mortality water samples. And so this is telling us that tire wear particle leachate is probably related to this phenomenon. Next slide, please. Our collaborator in WSU also did a parallel test with the tire leachate. And they found that when exposing tire leachate to coho salmon and chum salmon, all the coho salmon were killed, but chum salmon actually survived. We can click the slide to see the figure. Yes, thank you. So this is showing, right, like coho salmon is really susceptible to the tire leachate, and it's acutely toxic to coho. So the research question for me is to figure out what are the lethal toxicant in the tire leachate, right? Next slide, please. So the way we do that is to first make tire leachate from the, the tread of the tire rubber. We put them into stainless steel columns, put with some clean glass beads to disperse them, and leach them through a pump system for a whole day so that we can get liters, tens of liters of tire leachate. And then we do fractionation on tire leachate, use a physical chemical separation methods to divide them into different parts, because the tire leachate is chemically complex, right? We can see Usually in the mass spectrometer, we see more than 2,000 chemicals. So we need to simplify them to see which part is toxic to coho salmon. So the biological endpoint that we use is this photo in the right bottom corner. Those are the small, like juvenile coho salmon. In each tank, we can put 10 or 5 of them so that we can see the mortality. And when we prioritize a toxic fraction, we can put this fraction through to the high resolution mass spectrometer to do identification, see what are the chemicals in there. Next slide, please. So we did some like initial fractionation, right? Like to see the property of the toxicant. And we found that after centrifugation, the tire leachate is still toxic, so that we know the toxicant is in dissolved phase. It's not easily bound to particles. Click, please. And then we also have the tire leachate added with EDTA, which is the organic acid that can deactivate metals. And the tire leachate is still toxic, so that we know the toxicant is not a heavy metal. Click, please. And we also try to pass the tire leachate through cation exchange resin so that we can see if the leachate is cation or not. And turn out that the leachate is still toxic, so that we know the toxicant is neutral. Click, please. So with these properties, we can put our fractionation framework into a more detailed method called effect direct analysis. Next slide, please. So the effect direct analysis is basically going through HPLC fractionation and try to simplify our toxic extract. So we can see this is a figure that we put in the final manuscript. We go from the 2,000 feature, very complex tire leachate extract, and going through some initial purification step, and then going through a 3-column effect direct analysis. Finally, our fraction, like the final purified fraction, was pretty simple. Only we can see a few chemical features. And in that one, it is actually dominated by one chemical feature that has a formula of C18H22N2O2. And we can see in this photo, it's a pink magenta color solid. And when we dissolve this chemical to the fish tank, it will kill coho salmon like really fast in 2 or 3 hours. So this is our toxicant. Next slide, please. So we want to figure out what is this chemical. So we search this formula in literature and database to see if there's any tire rubber related chemical can match. However, we don't have this luck because it's probably a true unknown, right? Like you cannot easily find it in the previous studies. So I was assuming this is a transformation product from tire chemicals. It is not deliberately put in there. The assumption I had was for transformation products, usually we'll have the same carbon and nitrogen numbers, but we'll have different hydrogen and oxygen numbers. Based on this, I was able to find a chemical called 6-PPD. So it's a chemical with 18 carbon, 24 hydrogen, and 2 nitrogen. And if we search this chemical on Google, we can easily find them, and we can actually purchase that in pretty large quantities, right? We can see the photo left below, right? Like usually we can purchase that in kilos or even tons, because in all the rubber tire, about 1% of the tread mass is this chemical. So it's an antioxidant. And more interestingly, when I was searching for its transformation behavior, we found that there's one chemical they call the 6-PPD dinitron, has exactly the same formula as our toxic transformation product, right? So there's a potential correlation between 6-PPD and our unknown toxicant. So we purchased 6-PPD and did ozonation experiment. Click, please. Okay, that one didn't show up. That's fine. We actually did the ozonation experiment, and we found the same ozonation product that's matching the unknown toxicant in our tire leachate. So we can see from the LC chromatogram, the retention time matched, and in the high resolution mass spectrometer, the MS-MS fragmentation also matched. That means in the tire leachate and in the 6-PBD ozonation, we have the same thing. And also, we send this chemical to our collaborator, and they did an NMR analysis on this compound, and turned out that this is not the dinitron that the old paper suggested. Instead, it's called 6-PBD quinone. Click, please. So yeah, we can see this is a proposed pathway from the parent compound to this transformation product. Next slide, please. So we can see the video showing how similar the symptoms are in the creek as well as in the lab experiment. So from this creek exposure, we can see how the adult coho salmon is swimming in circles. And then if we click next, in the lab exposing like the pure chemical. Oh, okay, it didn't show up. Well, the juvenile coho salmon is generally swimming in the same pattern. I don't know why it's not showing up. Probably like a format issue, but that's fine. We can jump over this. Next slide, please. It's qualitatively that's from the video, and quantitatively we can see, in all the road runoff samples, this compound 6-PBD quinone were detected. And all of them are above the LC50 for coho salmon. And also in the creek water samples, those are the receiving water, right? Like 6 out of the 7 creek water samples, we can see 6-PBD quinone, and they were around the concentration of the LC50. And they were also detected in the California samples in Los Angeles and San Francisco, suggesting that this is probably a ubiquitous pollutant. Next slide, please. So recently we got a commercial standard for this chemical and internal standard. So that will allow more accurate quantification. We can use an internal standard method for that. Next slide, please. So the quantification method is based on spiking internal standard into the water sample and using a triple quad for the quantification. So this will be more easily available, like more people will have access to triple quad. And in this method, we are using 2 fragments that we can see from the figure, like a 215 and 187 as the qualitative and quantitative ions. Next slide, please. I'm going a little bit fast because of time. So we can see this is the method performance that we have with the internal standard method. So generally, the recovery was pretty satisfactory, and we have good sensitivity, usually in the pretty low nanogram per mil concentration for the instrument sensitivity. And also for the real samples, we have good LOQ, LOD for the real samples. We see that the suppression is usually the major challenge instead of the analyte loss, but we still can see pretty clear the internal standard is there. The compound is in the real, like a stormwater example. So this is still like ongoing work, and we hope to have this method development paper published in a few months. So yeah, this is basically what we are doing, and we hope that more and more labs and institutions can perform analysis on 6-PBD quinone. So thanks for your attention. Next slide, please. Yeah, if you have any questions, I'd like to answer in the Q&A session. Thank you.
Great. Thank you so much for a great presentation, Zhenyu. Like you mentioned, we're a little short on time for right now, so he'll be available for questions during our Q&A time from 11 to 11:30. Our next presenter is Dr. Yegi Dearborn. Dr. Dearborn is the owner and founder of Cell Analytical Incorporated, a California ELAP certified environmental laboratory in San Francisco since 2005, specializing in the analysis of microbiological pathogens in water, wastewater, and sludge. Recent project experience includes serving as the lead laboratory to 2 nationally certified sub-labs for the Water Research Foundation Direct Potable Reuse Phase 2 Pathogen Monitoring and Raw Wastewater Campaign from 2019 to 2021. Cell Analytical has been certified and approved to participate in many interlaboratory projects, including the EPA ESWTR LT2 monitoring for Cryptosporidium and Giardia, and the US EPA UCMR3 groundwater pre-screening survey for enteric viruses, US EPA method 1615, bacteriophage using US EPA method 1602, and indicator bacteria. Please help me welcome Yegi. Yegi, I think you need to hit *6 to unmute yourself there. Yeah, you're still muted. Can you start with a *6 to see if that fixes your microphone?
Good morning. This is Yegi Dearborn, and I will be talking about a modified method for detection of parasites in untreated wastewater. Before I get into the method, I would like to give a short summary of a background summary of potable or direct or indirect potable reuse in California, and also talk about existing protozoal methods and kind of figure out what made us use this EPA method for looking at parasites in wastewater. Next slide, please. So water reuse in California is regulated under Title 22 and 17 California Code of Regulations. Primary regulations require the pathogenic microorganisms are controlled. And in order to do that, in reuse, either groundwater is recharged through groundwater replenishment reuse project, which provides an environmental buffer for the reuse buffer to be added to the groundwater, or DPR, which is the planned introduction of the recycled water either directly into the public drinking water system or into a raw water supply immediately upstream of the drinking water plant. So so the idea behind this water reuse is that you're supposed to have a 12-log reduction of enteric viruses, 10-log reduction in Cryptosporidium giardia, so that you will have a 12, 10, 10-log reduction for indirect potable reuse. The requirement of the regulation also states that water that is treated should have treatment train that consists of at least 3 separate processes. And each process are given credit for, but no more than 6 log reduction in any given process. We have in 2021 a new direct potable reuse framework for regulation, which has made the log reductions far more stringent than what it's been used for indirect potable reuse. And the log reductions consist of 20, 15, and 14 log reduction. So I'll be going on my 3rd slide, which is the background on Water Research Foundation number 4952 DPR2 project. This project from Water Research Foundation was designed to look at the pathogens in raw wastewater. It's funded by California Water Board, and it was initiated in November 2019. It ended at the end of January 2021 for the actual laboratory work. The purpose of this was to better define pathogen concentration in raw wastewater so that we can understand how the log reduction is actually taking place per regulation that requires that. The other thing we wanted to do with this project was to establish a multi-laboratory validation method to be evaluated, optimized, and campaign studies being done almost simultaneously at the same time. We looked at protozoa, crypto and giardia in raw wastewater. We looked at number of viruses, enteric viruses in wastewater, and right around April, where we were in the midst of the pandemic, we added SARS-CoV-2, which is the agent for COVID-19, and looked at methods to harvest or isolate this organism as well from the raw wastewater. Next slide, please. Again, the important thing about this particular work we did was it was a multi-laboratory validation. It is always a good idea to have something done by multiple laboratories and it's reproducible. We were the lead lab on the project. BCS Laboratory of Gainesville, Florida was the method development and monitoring lab. Scientific Method in Granger, Indiana was a monitoring lab. And before we initiated this campaign monitoring, initial method evaluation were done by BioWare Laboratory in Benicia, California. Next slide, please. So we have currently a couple of approved methods. One for detection of protozoa in water. The one that most of us are familiar with is EPA 1623 or 1623.1, which was a uniform testing criteria that was developed by US EPA for nationwide long-term treatment 2 monitoring. Pretty much this was for drinking water or sources of drinking water, surface water that was a source of a drinking water or groundwater that is under the influence of a surface water. Depending on what the source is, approximately 10 to 50 liters of water is filtered or concentrated, and the concentrated pellets range from 0.1 mil to 2 mil size, depending on the volume filtered. Usually, crypto and giardia are recovered through analysis of a 0.5 mil portion of the pellet size, and we use immunomagnetic separation beads that rely on antibodies for detecting these organisms. The method is really good and it's really feasible for source water and finished drinking water. And it's a FOA, Field of Accreditation, offered by ELAP as FOA 129. This method, however, is not feasible for checking at raw wastewater. Next slide, please. So we looked at another method by US EPA called US EPA Method 1693, which was developed to look at crypto and giardia from a secondary disinfected wastewater. And the method also very much relied on either centrifugation of 1 liter sample or filter 10 liter sample. Concentrated pellet volumes were much higher in size, 2 mil process, again in 0.5 mil portions for immunomagnetic separation. So you can literally look at this method. For each sample, you would look at 4 slides per sample. Now, this method did not directly address the complexity of raw wastewater either. Next slide, please. And the reason for that is when you look at the matrix has defines everything we do in our work here. So when you look at a disinfected secondary wastewater on the left, a wastewater versus the raw wastewater we were testing during the DPR2, you will see the difference. The raw wastewater is incredibly complex, and it's not the same as a disinfected wastewater that's already gone through chlorination and cleanup stuff. Next step, please. So the DPR2 optimization of the method 1693 involved a few tweaks and modifications to EPA 1693. So we ended up doing, taking 1 liter of this very dark raw wastewater and in each event, we added a color seed to the 1 liter of wastewater. And color seeds are oocytes and cysts that are inactivated and permanently labeled with a red fluorescent dye. We went ahead and concentrated the pellet volumes. We ended up getting anywhere from 10 liter, I mean, we get actually up to 10 liter of pellets. But on this project, we decided to look at 4 mil pellet size. So for immunomagnetic separation, prior to addition of the beads, after concentration, we added a clay material called kaolin, and it's supposed to take out a lot of the fats and other things from the raw wastewater, so the organisms and beads can find each other in some ways. 4 mil pellets was equivalent to 8 immunomagnetic separation slides and samples, and this increased the probability of detecting native cryptosporidium in raw wastewater. And color seed spike recovery provided assurance that the method worked every time. Next slide, please. So when you look at the immunofluorescent assay, there is nothing different from color seeds versus the actual native samples. They all look the same under immunofluorescent microscopy. Like if you look at the top row of the immunofluorescent image that I have, it's for Giardia, and the bottom is cryptosporidium. It goes through FITSI on the left side for looking at the membrane, how they light up with a proper FITSI antibody. Then in the middle, you look at the nucleus, how they are lit up by DAPI. And then you have a differential contrast microscopy that shows the internal structure of these organisms. The only difference between the native and the color seed is that under the Texas red, you'll see a bright red color if it is a spiked color seed, versus if it's native, it will not light up under the Texas red. Next slide, please. So we use this technique on 5 California utilities, approximately 120 samples representing untreated wastewater from approximately 10 million people. And the data showed that cryptosporidium, on the average, you can detect 27 oocytes per liter of wastewater, and with a 39% recovery rate for the color seed. And Giardia is more abundant. You get 4,500 cysts per liter on average, and a 40% recovery rate on average. Next slide, please. So this method, 1693 modified, was validated rigorously among multiple laboratories. We have currently, ELAP currently offers EPA 1623 for drinking waters, and laboratories need to be assessed for this field of accreditation. EPA 1693 modified would be a nice addition or a new field of accreditation for wastewater. It will provide a uniform data that can be shared among various agencies. We have in one end DPR regulations that are going into effect soon, and requires some testing that would be done regarding all these organisms that have to meet log reductions. And then drinking water regulation is going to be adding a chapter in Title 22 for direct particle reuse, and drinking water regulation agencies would also be interested to see how data comes out from DPR projects or DPR direct particle reuse treatment systems. So we think having a new field of accreditation for this methodology would be very useful in future, looking at the DPR and drinking water usage. Next slide, please. Our project team included Water Research Foundation, California Water Board, and Water Research Foundation Coordinating Committee. Trussell Technologies, that were the project managers on this project, carried most of the project management. Cell Analytical, which was us, and DCS Laboratory, we conducted primarily most of the monitoring for the duration of this campaign monitoring. And I believe very quickly we're going to see documents coming up that will be discussed by Trussell Technologies and Water Research Foundation, summarizing all the data that was gathered on this very interesting campaign. And the reason I put up the name for the project ID on this slide is these documents are available on Water Research Foundation site. You can access the Quality Assurance Project Plan. You can access the methodologies that are already published and available. And if you have questions, you can always contact me directly by cell number or my phone number, and I will be also available to answer questions during the question and answer session. Thank you for listening, and I hope I managed to provide the slides as I see them, because there was a lag in seeing the slides and providing the presentation. Thank you.
Thank you, Dr. Dearborn. We are out of time for Q&A for right now, so we will do it at the end. Up next, we will hear from Dr. Charles Wong. Dr. Wong is the department head in chemistry at SQUIRP. His research interests include developing novel methods for constituents of emerging concern, including pharmaceuticals, polyfluorinated alkyl substances, metabolites and degradants, and microplastics. He also studies the sources, fate processes, and ecotoxicological consequences of these chemicals through bench to mesocosm scale controllable experiments. And
okay.
temperate implement through Oh, hi, Charles.
Hi. Are we? Am I? Can you hear me?
Hello.
Yes,
Hello?
we can, Charles.
Okay,
Yeah,
great. Okay.
We can hear you.
Okay, let's go ahead and get started. It's a pleasure to be here. I want to spend a couple minutes to talk a little bit about one of the things we've been doing at SQUIRP, which is our intercalibration study for microplastics in drinking water. Next slide, please. Okay, so the impetus for this is a couple pieces of legislation that were passed that basically requires monitoring and strategies for monitoring microplastics in the environment, and particularly in drinking water, starting this year. And needless to say, in order to do this, there needs to be measurement methods that have been vetted and adopted and approved. And these methods need to be both scientifically sound in terms of being able to do what they do, but also they need to be feasible in terms of both technological feasibility and logistical feasibility. Labs that would monitor for this basically have to be able to do this. Next slide, please. Now, this is a pretty significant challenge, because typically developing methods takes a very, very long time, especially for something that's as new as microplastics in terms of figuring out how to measure them. Currently, right now, it's people basically kind of use whatever they want, so it's difficult to compare data measured from one method versus another method. We have to figure out what kind of methods we really want to use and how to go about doing that kind of standardization, including how to manage the data that comes out of it. Perform inter-lab studies to basically quantify how the method works or doesn't work, and then refine these methods based on the data that you get in order to reduce the variability. Rinse, lather, and repeat. This takes a long time, and the legislation calls for a rather short time period. And as I said, microplastics is a fairly new area, so it's not really clear what's important to measure. Is it the size of the particles, the shape, the type of material they're made of? We currently are also running a health effects workshop to try to figure out what is the things that matter with regards to effects of microplastics and how much matters, so that the measurement methods could know what to aim for. Next slide, please. So in a nutshell, our study is basically designed around an intercalibration blind exercise. So we create samples where we know the composition, but participating labs do not. And they analyze these by various candidate methods using a common playbook, a common SOP. So we eliminate that as a source of potential variability. And we quantify a couple things. We quantify accuracy, basically how close can you get to the middle, as a function of all sorts of things such as size and shape and so on and so forth. We also quantify precision, how close are basically each of your shots to each other, because if they're very precise and they're very repeatable, but they're off, you can correct for it. And in fact, some of our data does suggest that could be indeed the case. And this will allow us to identify basically the capabilities and the limitations of the technical method on a number of different fronts. We have replicates, so you can see see accuracy and precision from the same lab. You can see it across different laboratories, and you can also parse it out from things like very experienced labs to very novel labs, which is important because for monitoring purposes, a lot of labs are going to be new to this. So we want to make sure we have methods that work not just for the best labs in the world, but also for labs that are new to this, and try to quantify how quickly they can come up to speed. And of course, because we're interested in logistics, we're also interested in understanding, well, how long does this take and how much does it cost? Because this needs to be something that's manageable. Next slide, please. So the kind of products we're getting from this are basically the methods to be able to do this, candidate methods we would propose, the standard operating method procedures for these methods that we would refine based on our results, and also an accreditation process for labs that would be doing this for monitoring purposes. And in a nutshell, we basically have all three of these for drinking water. Next slide. So what I'm going to do now is give you a very high-level discussion of what the study is about. Obviously, I can't talk that much about it in 10 minutes total time. I'm also happy to answer questions. Basically, we have 5 major methods, candidate methods that we're using, ranging from visual microscopy to a couple different types of spectroscopy to a pyrolysis GCMS method. Next slide, please. Now, as far as the blind samples go, there are a number of different types of plastic polymers in there. Some examples are things like polyethylene and so forth. They range anywhere in size from 1 to 1,000 microns, organized in 4 size fractions. This is the first study that, to my knowledge, where we basically would go down all the way to 1 micron, which is very, very challenging technically. There's a number of different types of shapes, such as spheres and fibers and pellets and fragments. And also unique to this particular intercalibration study is that we have some false positive materials, things that visually look like synthetic polymers, but actually aren't. So things like sand and natural fibrous material, various types, basically to try to confound analysis and see if people can pick up the real synthetic particles from basically all the stuff that would normally be in a typical sample. Next slide, please. Next slide, please. Thank you. So we have a lot of participating labs from academia, from various levels of government, from a number of different private sector industries. These range from very experienced laboratories, leaders in the field, to very novice laboratories, and we have a lot of robustness in terms of numbers of labs per method. Next slide, please. This is the kind of general layout of how the lab work works. So we've got blind samples that get sent out to the labs. They would basically process these samples in the laboratory to collect the particles and get rid of all the stuff that's not particles. They would use visual microscopy to identify and figure out, categorize particles and take pictures and figure how big they are, and then basically confirm a subset of these using various types of spectroscopic and mass spectrometric techniques. Next slide, please. So with regards to the simulated drinking water matrix, the lab processing basically amounts to separating what's in each of the blind samples into the various size fractions through sieving and filtering, and then analyzing basically what you've got. Next slide. So where are we and what's to come? Well, as I said, as we currently stand right now, we've got all of our products in terms of methods, in terms of refinements to our SOPs based on what we learned, and also in terms of the kind of accreditation process that would be appropriate for a monitoring program. And that's been submitted to Scott Coffin of the State Water Board. He's the contract manager for this particular project. We're basically kind of dotting I's and crossing T's for his public presentation that will be later in the summer. Yes, despite you know what and massive delays and labs dropping out, we are still on time for legislative requirements. In the next little while, we'll be developing the ELAP lab accreditation processes in conjunction with ELAP, as well as what we're currently doing now is disseminating the data and the information into appropriate peer review manuscripts in a special issue of the journal that we are working forward. I think that's the last of my slides, so I don't know if there's time, but if there is, I'll be happy to answer any questions, or either now or at the Q&A period later on.
Great. Thank you so much, Dr. Wong. That was a great presentation. We might have time for one question if anyone wants to pop one in the chat really fast. Thank you for a quick presentation, helping us keep on time today. There is a slight delay with the audience, so I'll give them just a second to see if anyone has any questions. Okay, well, if you guys want to think of your questions and put them in the chat, then we will definitely ask them to Charles at the end of the morning. So we will go ahead and move on to our next presentation. Our next presenter is Dr. Susanna Thoreau. Susie Thoreau is a senior scientist at the Southern California Coastal Water Research Project. She focuses on algal bioassessment and the use of molecular methods in routine bioassessment and biomonitoring. She's also the lead for the California Molecular Methods Work Group. Thank you, Susanna, for joining us this morning.
Hi, everyone. Thank you so much for having me. I'm excited to be talking to you all today about our efforts here in California towards standardizing molecular methods approaches and how these efforts align with those in the broader national and international community. So you can go to the next slide. So first off, I wanted to begin with a little bit of background regarding what we're talking about when we talk about molecular methods. So molecular methods involve the collection and analysis of DNA and sometimes RNA from the environment. We often refer to this as environmental DNA or eDNA, you might have heard it called, and these types of samples can include anything from water to soil and sediments, biofilms, and more. And additionally, we use these samples to identify target organisms that can include anything from microbes to mammals. And often when we're collecting these samples, our samples include both intracellular and extracellular DNA, so DNA that's found both inside and outside of a cell. And that ends up being really important when we're selecting our analytical techniques and when we're approximating how quickly this eDNA might degrade in the environment. Next slide, please. So there are some key advantages to adopting a DNA-based approach for biomonitoring and bioassessment. Typically, we rely on traditional microscopy-based methods that are often quite time-intensive. They have limitations in our ability to differentiate cryptic species. The sampling can sometimes be destructive, which is problematic for targeting some sensitive or endangered taxa. And lastly, to collect an organism, you have to have the timing of your collection spot on in order to capture the organism you're hoping to monitor. In contrast with our eDNA-based approaches, it helps address some of these limitations by, in general, being a little bit faster increasingly more affordable. It can also be very sensitive, repeatable, and scalable. And sampling is minimally invasive, and you can detect traces of organisms long after they've already left a sampling location. Next slide, please. So what are some of the types of DNA-based analyses that you might choose in order to monitor your target organisms? Well, that really depends on your research question. So for example, you might choose quantitative PCR or its close relative digital PCR to quantify a target organism or a target gene to answer questions like how many pathogen markers are present in my sample. If you're interested in identifying an organism, you might choose DNA barcode sequencing, where you're using a single section of a gene called a barcode to determine the taxonomic identity of that organism and answer questions like, is this a zebra mussel or a quagga mussel? If you want to move beyond a single organism and instead identify multiple organisms all at one time, you perform community profiling via DNA metabarcode sequencing, wherein you're sequencing DNA barcodes from multiple different taxa all at the same time. And that helps you answer questions like, what is the biodiversity of fish in my sample? So these are all the different types of analytical approaches that we might be using these molecular methods for. Next slide, please. You can click a couple. Get to the next slide. Awesome. All right, so there are a couple of different applications where DNA-based approaches are really becoming more and more popular. And so these include things like monitoring and surveillance for invasive and endangered species. As I mentioned, the key advantages here are that now we're having really sensitive and non-invasive sampling of these critical organisms. Also for harmful algal bloom and pathogen tracking, again, very sensitive and therefore early detection of these organisms that we want to be monitoring for before something like a toxic bloom event occurs. It also allows for remote sample collection. So there are now apparatus where you can deploy and then collect your DNA samples and bring them back to shore and analyze the samples that you've collected there. And somewhere where it's becoming increasingly popular here in California to use DNA-based approaches is in bioassessment and biomonitoring. So with this, you're looking for your key indicator taxa that you normally would analyze using microscopy-based approaches. Now we're using DNA to perform those taxonomic analyses, and it's really helping to alleviate what we call this taxonomic capacity limitation, where it's become harder and harder to access some of those trained taxonomists for generating that taxonomy data that is critical to performing those biological assessments. Okay, next slide. So as I mentioned, one area where California is really leading the field in the adoption of molecular methods is in bioassessment, and in particular for the collection of algae samples for bioassessment. So the pipeline for generating algae taxonomy data looks pretty straightforward. You start with an algae sample that gets collected in the field, you bring it back to the lab for DNA extraction, you then amplify one of these DNA barcode regions for DNA metabarcode sequencing, you perform bioinformatic analyses, assign taxonomy, and then use this resulting taxonomy to calculate biological index scores, which may or may not be similar to the biological index scores that you generate with the morphotaxonomic data. This all seems pretty straightforward enough, right? It should be pretty easy to incorporate these molecular approaches. Next slide, please. But in fact, as many have found before, there are currently no standardized approaches for this type of DNA metabarcode sequencing. So when we want to select our approach for each step in this workflow, we're pretty overwhelmed with decisions, and all of these decisions have the potential to impact our resulting biological assessment outcomes. So this includes something like, what DNA preservation method should I use? Are all DNA extraction kits created equal? What are the best DNA barcode primers to choose for my target organisms? Does the bioinformatic pipeline matter? What DNA reference library should I use? And lastly, of course, are our assessment outcomes the same, depending which of these different approaches we use? Let's see. So what I'll be doing today is walking you through a couple of the pilot studies that we've performed to help us optimize both our DNA barcode primer sets for sequencing algal communities, also comparing different DNA extraction kits, and lastly, how our choices in our bioinformatic pipelines in clustering our data and assigning taxonomy can all impact our eventual assessment outcomes. Next slide, please. So for the first pilot study that I want to introduce you to, we were looking to adapt the Algal Stream Condition Index, or a biological index that was published in 2020 for use in California wadable streams that targets stream algae. So our study design involved taking the composite algae sample that gets collected, splitting it for both that microscopy or morphotaxonomic analyses, as well as our DNA metabarcode sequencing, and then performing bioinformatic analyses where you curate through all of your raw DNA sequences, and then you assign taxonomy, identify who all the different species are present in your sample, and then eventually calculate your biological index scores. For this study, we were interested in comparing a number of different DNA barcode primer sets. So we were looking at 2 different 16S primer sets, which allow us to look for the cyanobacteria. Then we were using 2 different 18S primer sets, allowing us to look at different diatoms and soft algae, and lastly, 1 diatom-specific RBCL primer sets. So in total, when we combined all these different primer set combinations, we had 12 different DNA barcode region outcomes that we were evaluating for how they performed in capturing that algal community. To jump forward right into the results, what we found was that all these different DNA barcode primers that we were evaluating all picked up different components of that algal community. So the more of those DNA barcode primers that you were using and layering on top of each other, essentially you were getting better agreement with what our morphology data was telling us, both in terms of who was present and what those biological index scores were saying about biological condition. Through this study, we also found that many of the reference libraries lack necessary reference sequences for key algae species, especially in California. We have great diversity of algae, and unfortunately, we miss a lot of those taxa if they don't have a reference sequence in these global DNA reference libraries. So what we're doing now is joining forces with Cal State San Marcos and isolating and sequencing some of these priority algae taxa that are key indicators of biological condition. Okay, next slide, please. So the next pilot study that I want to tell you about was spearheaded by our colleagues that are part of the European standardization effort called DNA Aquanet, and they invited us to participate as well. And there were 10 labs in total that all participated in a DNA extraction kit ring test, they like to call it. And so in this study, we were aiming to determine the impact of the DNA extraction kit on resulting algal community composition. Each of these 10 labs extracted the same DNA samples with both their preferred DNA extraction kit, and then they performed the extraction again with a standardized DNA extraction kit. What we found in this study is that when all labs use the same DNA extraction kit, the results are really similar. But when all labs use their preferred DNA extraction kit, there is variability introduced into the resulting algal community composition. Thankfully, at this point, the variability that gets introduced by those DNA extraction kits is small, and it was not impacting the eventual index scores and assessment outcomes. But that might not always be the case depending on different sample types and different extraction kits. So moving forward, the incorporation of something like internal positive controls and mock communities is going to be one of the ways that the field is hoping to standardize these approaches so that multiple labs can use their DNA extraction kit of choice, but that we can ensure that the resulting assessment outcomes will be consistent across different labs. Okay, next slide, please. And so the last pair of pilot studies I wanted to tell you about, we're looking at the impact of the bioinformatic pipeline, again, on the resulting assessment outcomes. And so we had a couple of different studies that we were involved in. One that was, again, part of a broader international effort where SCRP, along with NOAA and the EPA and a university in Canada and one in Australia, all took the same DNA data set and then passed it through our individual bioinformatic pipelines and then compared the results. And then similarly, we had another comparison study where we again took the same DNA sequences and passed them through 2 different bioinformatic pipelines. If you're familiar with them, they were called CHIME and MOTHER. And then we used different clustering thresholds, different ways that we lump all of our DNA sequence data together before we assign our taxonomy to see how much of an impact that would have on our resulting community composition. If you click forward 1 slide. Just jumping right into the results, as you might expect, DNA pipelines really do matter. And similarly, the DNA thresholds that you're clustering your sequences at really does matter. And in all of these different bioinformatic comparisons, what we were finding that consistency was key. So again, there's some variability that gets introduced depending on the various components of these bioinformatic pipelines and how you go about applying them. But then when we start to institute some thresholds and allow for greater consistency, we minimize those biases that get introduced by these different bioinformatic pipelines, and it again ensures that there's high quality and consistent data getting calculated by different bioinformatic pipelines from different groups. All right, thanks. Next slide, please. All right, so there's been great progress now in beginning to establish a foundation for the standardization of these protocols in California and beyond. And to help coordinate the efforts, we now have what's called the California Molecular Methods Work Group, a work group within the California Water Quality Monitoring Council that is focused on developing these standardized protocols, performing intercalibration exercises, and also sharing resources like DNA reference libraries among its users. This is a really diverse work group. Membership is open to anyone that's interested, and staying up to date on both DNA methods and DNA standardization protocols. Just shoot me an email if you're interested in joining. One of the things that we're also focused on doing is making sure that all the efforts here in California are aligned with those both in the broader US and the international communities. Next slide, please. So the Molecular Methods Work Group has already been working over the course of the past 2 years on developing a series of standardized protocols and best practice documents that are focused right now on water eDNA sampling, field sampling best practices, and metadata reporting standards. These protocols were all drafted in collaboration with management and stakeholder groups, and I think that really is the key to their success, and that's why I love the title of this conference, Quality Through Collaboration. And it really just helped ensure that we had high quality and a lot of diverse voices going into the creation of these protocols. These protocols are now being integrated into statewide monitoring programs, and in future years will be focused on developing additional SOPs or standardized protocols for both the lab and bioinformatic analyses at the parts of that pipeline. Next slide, please. One thing I wanted to mention was that when we were developing these protocols, we had a lot of conversations among our work group as to which approach is best in terms of developing either what we call these best practice recommendations or more stringent or strict protocols that specify exactly what different steps in the protocol call for. As you can imagine, for best practices documents, some of the pros are that it allows for greater flexibility, a little bit more of a choose your own adventure, but it also can allow for greater error. And an example of this would be using a DNA extraction kit that includes a bead beating step. In contrast, a more stringent protocol might say something like you must use a QIAGEN power soil DNA extraction kit. So both of these two approaches has their pros and cons. But if you go to the next slide, what we're seeing is that among both in California and the broader international community, they're really beginning to converge on the use of best practice approaches when possible, and incorporating target benchmarks using, as I mentioned before, internal positive controls or mock community performance as a way to ensure this comparability and high quality of the data. So this approach emphasizes the importance of metadata reporting for documentation and future reproducibility, and also allows for adaptability in the face of rapid technological innovation, which we're really seeing in the DNA field. So we're seeing this approach right now being used both in Canada and in Europe for their water eDNA sampling protocols. But we do also anticipate that certain steps in this pipeline, for example, the DNA reference library that you're choosing, that's something where we might see some more stringent guidelines somewhere down the road. So lastly, I would just like to conclude by saying that we are seeing the use of these DNA-based approaches for environmental monitoring growing rapidly. There's an increased focus on standardization and best practice recommendations, and that we're optimistic this is going to help accelerate the adoption of DNA-based approaches. And the quality of these future standardized protocols really does hinge on the successful collaboration between researchers, agencies, and stakeholders. But because of California's unique collaborative environment and organizations like ELAP, we're really able to serve here in California as a leader, both nationally and internationally, in the development of these standardized approaches. So thanks very much for the opportunity, and I look forward to the discussion.
Great. Thank you so much, Susanna. We think we do have time for 2 quick questions. One that came in, have you looked at distinguishing algal toxin using this method, or is it only taxonomy?
Yes, there are great opportunities for looking at algae toxins. You can do it either through DNA metabarcode sequencing. You can also be doing it through qPCR or digital PCR. There are some groups that are already pioneering some of those approaches. I'd be happy to chat with anyone more if they want to tag me in the Slack. I can point you towards some resources, but it's exactly the right type of approach that you could be using. Yeah.
Perfect. And then one other, what do you think is the biggest challenge in getting eDNA used in the California lab community?
Oh, that's a great question. I mean, I think really what did spearhead part of the creation of the molecular methods resource is that we weren't alone and that there really are just so few, if any, standardized protocols. So I think that the more we talk about it, discuss these options, and provide training opportunities for folks to get comfortable using these approaches, hopefully they'll become more popular, and that the protocols that we're developing will only get stronger as we have a broader user base. So.
Great, thank you so much. And like Susanna mentioned, she's on our Slack channel, so you're more than welcome to chat with her there. And I believe she will also be available for questions from 11 to 11:30. Next up, we would like to welcome Charles Nesland. Charles, or Chuck, is the Scientific Officer for Eurofins Lancaster Laboratories Environmental and PFAS Practice Leader for Eurofins Environmental Testing US. Chuck has worked in environmental analytical chemistry for over 36 years and works out of Lancaster, Pennsylvania location. He is a subject matter expert in HRMS analysis and PFAS analysis. He is responsible for identifying and framing trends in analytical testing and equipment. Chuck initiates new methodology and directs research and development. He has a Bachelor of Science in Chemistry from the University of Pittsburgh and 2 years of graduate study credits in organic chemistry from the University of Pittsburgh. He's a member of the American Chemical Society, the Chromatography Forum of Delaware Valley, Air and Waste Management Association, the Society of Environmental Toxicology and Chemistry, and Sediment Management Work Group. Please welcome Chuck.
Thank you very much. Can you, just to confirm, can you hear me okay?
Yes, you sound great.
Okay, thank you very much. There's a little bit of a delay, so I'll ask for the first slide, please. So today we're going to talk a little bit about EPA 533, and the question, once we get the first slide here, when the operative question here is, why did we need another PFAS drinking water method? I mean, wasn't one enough? And let's face it, in the face of the rapidly changing landscape with regard to PFAS, do we need any more variables, any more confusion in what we're doing or what we're expected to do? I think the first thing we wanted to talk about here, if we could go, that's fine. If you could go to that next slide, that'd be terrific. Is a methods timeline, and we'll just to sort of set the background here, so that if we look at this methods timeline, when we first started testing for these chemicals in environmental matrices, our methods were based off of manufacturers' methods and classified as typically user-defined methods and that were certifiable under EPA with a method reference like 8321, but there wasn't an EPA-defined method. Then in 2009, late 2008, 2009, we actually had EPA 537 version 1.1, the drinking water method for doing PFAS, looking at a list of 14 PFAS compounds, and principal in that list were PFOA and PFOS. And then that was done really in preparation of, even though it was quite a few years before, but it was done in preparation of for use under UCMR 3. And in UCMR 3, if you remember, we covered 6 PFAS chemicals, 6 principal ones, which are still large topics of concern nowadays also, but to assess the drinking water across the U.S. And then we went for, throughout when PFAS really started hitting getting big, if you will, and going, we started evolving into things beyond drinking water and going into wastewater and solids and started to evaluate tissue. And so we really expanded on these user-defined methods, which we then ultimately called 537 modified. So, but that's not today's topic. But then as we moved along, you ask, well, why this new drinking water method here in 2019? That was 533 that was issued at the end of 2019. Well, in part because of this rapid emergence and turbulence, if you will, within the industry or within the environmental industry for evaluating and monitoring PFAS, became evident that PFAS were not, the PFAS that we needed to cover could not be adequately covered by 537.1, as well as I think there was some recognition, and we're going to talk about the methodology, that there was some recognition on EPA's part with regard to the methodology and the quantitation scheme and the like, that we could experience and see improvements and make it a better method than 537.1. So if we can go to the next slide, please. So on this next slide, I give some examples of state drinking water limits, and I put in there into this list California. California has notification levels for PFOA and PFOS, 5.1 for PFOA and 6.5 for PFOS, which are relatively low if you compare to limits that are in other states across the U.S. And I show a couple other ones there. But a difference is, in this case, for California, these are notification levels, and we're certainly looking at going to lower levels. But a state like New Jersey, which was actually one of the first that actually established a statewide MCL. So an MCL, so it has actionable consequences for exceeding those limits, a 13 PPT for PFOS and 14 for PFOA. They also have one for PFNA, and actually I think are probably the only one of the few across the U.S. that established one for PFNA. And then you can see some other, just to sort of give you a flavor of what's going on across the rest of the U.S. Limits that have been proposed and those that are either MCLs or having been proposed as MCLs. You can see Michigan has propagated those. But in general, we're looking at, for drinking water, groundwater limits, we're looking at levels that are at low teens and single digit, mid to upper single digit kinds of PPT limits for PFAS. Next slide, please. So on this next slide, I talk a little bit about the Safe Drinking Water Act and UCMR 5. So, we had a couple things going on with regard to the creation and implementation of a method like 533. And one of those was we needed a method to support PFAS, the additional PFAS that we felt we needed to evaluate as a part of UCMR 5. Now, one of the changes with UCMR 5 is that as opposed to during UCMR, previous UCMR, where our threshold was water supplies that had customers upwards of 10,000 and above, or at 10,000 and above, that limit, that threshold has been lowered to 3,300. So we're looking at, and we'll be collecting data on a much broader swath of water distribution networks throughout the U.S. But as a part of this, to add to the list of compounds that could be covered by PFAS, needed a methodology that was going to be able to get what we oftentimes refer to as the short chain acids, or the short chain PFAS, which admittedly, and if you look at the text in the previous drinking water method 537.1, is that they admittedly say that they're not able to recover and perform adequately for things like PFBA, which is the butanoic acid, and PFPEA, the pentanoic acid. So we needed a methodology that could not only do those short chain acids, but could do a more expansive list of compounds and include some compounds that in between the time that 537.1 was created and this the advent of 533, a lot of work was done by commercial laboratories in coordination with work at DOD sites and like, where we started looking at other chemistries like fluorotelm or sulfonic acids and the like. Next slide, please. So on this next slide, I give a breakdown of the compound list between 537.1 and 533. And now the uniqueness is that to cover all of the compounds, because 533 is not exactly the list of 537.1 compounds plus a few. It is in fact most of 537.1 plus a lot, plus quite a few more, but there are several that are in 537.1 that are not in 533. So to cover all of these compounds, this total list of 29, you'd actually have to use and perform 2 analytical methods to be able to cover that total list of PFAS. And you can see here, and I know the print's a little bit small there, but you can see 533, which is for each of these boxes. It's the far right column in each of the 2 boxes. 533 has a much more expansive list. We can do it. We can do the butanoic and pentanoic acids, so that's a C4 and C5 acid, considered short chain acids. Also includes some additional sulfonic acid, perfluorosulfonic acids, more so than what was, I think there are only 3 of those included in 537.1, and then also goes to some fluorotelmer sulfonic acids, typically seen as used in AFFF kinds of formulations, which have certainly impacted groundwater, which is then of course used for drinking water supply, and then also brought in some additional, in addition to a couple of the compounds that were put in 537.1, these perfluoroalkyl ether carboxylic acids, which is a new and different chemistry, series of compounds that are being used by manufacturers for different fluoropolymer production processes. So 533 holds the promise of being able to do a more comprehensive scan of PFAS chemicals. Next slide, please. So on the next slide here, I just have another breakdown to sort of compare between 533 and 537.1, some details of the analysis of the analytical parameters, and the 2 key items that I really want to point to here are that for 533 and 537.1, they both use something called solid phase extraction, which is taking a small amount of a sorbent, and the sorbents can be of different chemistries, and you pass the water through those sorbents, and your compounds of concern adhere to those sorbents while the water passes through, and you then use, in this case for PFAS, we use organic solvents like methanol to elute the PFAS off of those sorbents to then go on to our analysis. Well, the chemistry of the sorbents that are used between the 533 and the 537.1 are pretty different. The 537.1 uses something called, and you see it about 4 rows down, called a SDVB, stands for styrene divinyl benzene. The basic thing to recognize or know with that is that it essentially operates on nonpolar interactions. So it takes advantage of that long carbon fluorine tail that's a part of PFAS chemicals. But if you think about this, taking advantage of the hydrophobic nature or those long carbon fluorine tails, so then theoretically the longer the tail, the better it's going to extract it, right? And also conversely, the shorter the tail or the shorter the molecule, the less effectively it'll extract it out of water. That's why these short chain acids like the butanoic acid and the pentanoic acid didn't work as well by the 537.1. Instead, 533 uses a chemistry which, if I may say so, many of we commercial laboratories have been using for 3, 4, 5 years prior to 533 coming out on our own user-derived methods, because it takes advantage of the functional head on the PFAS, so a carboxylate anion or a sulfonate anion, and that's what it latches onto. That way, any other organics that might be in that sample, even though we're talking drinking water, so there shouldn't be much of any organics there, any other organics or possible competitors for active sites on that sorbent, it doesn't matter, because the wax, the weak anion exchange, which is what wax stands for, grabs onto that functional head and doesn't worry about the carbon fluorine tail so much. The other thing that 533 did is that it used, again, a technique for our user-derived applications that we've been using for a number of years. It used isotope dilution. So isotope dilution, and if we could go to the next slide, please. Well, and actually I jumped ahead of myself here a little bit, because on my next slide I talk about the solid phase extraction. So just to reiterate, to not be too redundant, but solid phase extraction, I've got a decent graphic here that shows water going through, but the big difference is the chemistry, using hydrophobic interactions versus the weak anion exchange, which takes care of that functional head, the carboxylate or the sulfonate moiety on the chemistry. And I'll tell you what, as soon as you get to this next slide, why don't you just bump it to the one after, and it would be slide number 8 in the title. Go to the next slide right after this one, please. So we're going to talk about the isotope dilution. Isotope dilution is the other functionality. Next, 2 forward. So if you could please. One more past this one, and then you'll be good. Thank you. So it would be isotope dilution. Now, isotope dilution is a technique. It's not really so new. It's sort of new to PFAS, although, like I said, many of we commercial laboratories have been using this for our user-defined methods for many years. But those of us that have experience in high-res mass spec work, where we're doing, back one slide, please, where we're doing high-res mass spec work and we're using isotope dilution for that high-res mass spec work in the dioxin and furan analysis, are using this isotope dilution technique. So isotope dilution is where we're able to chemically synthesize a compound that, in the example I have on the screen here, PFOA is a target compound by 533 or 537.1. The compound that was on the left there is a carbon-13 labeled ice analog of PFOA. So that carbon-13 analog of PFOA, it extracts like PFOA, it chromatographs like PFOA, it will respond to potential interferences much the same as PFOA will. So it essentially mimics PFOA in virtually all of its activities. But because in the example I have here, there are 4 carbon-13 atoms present, that means my carbon-13 PFOA weighs 4 AMU more than my target PFOA. So with my mass spec, I can tell the difference. So if I spike this carbon-13 labeled PFOA and other carbon-13 labeled analogs into my sample prior to extraction, at the very end, when I go to determine my PFOA concentration, I can calculate a recovery for this carbon-13 PFOA, and if it only recovered at 60 or 70%, well, then I know that my native PFOA also only recovered at that level, and I can use that to concentration correct. Next slide, please. So it can give me the best accuracy and precision in the analytical application that we use. And then this last slide is just sort of a summary of this feature, which I think is an important feature of 533 about the isotope dilution. These isotopes, another name for them is an extracted internal standard, and these compounds, so they have a dual functionality. So it's not so much that it's a carbon-13 labeled compound, that's an important feature, but it's that you use the carbon-13 labeled compound as both a surrogate and as an internal standard. So it's got multiple functionality, and like I said, the ideal situation is we've got a 1-for-1 pairing of carbon-13 and the other, sometimes they're deuterated compounds, but carbon-13 or deuterated compounds, 1-to-1 pairing between those and your target analytes. And with that, next slide, which I think is the last one. Take any questions if we have time, or wait for any of them at the question and answer session. So thank you very much for your attention, and thank you very much for inviting me here today.
Great. Thank you so much, Charles. We do have one quick question I think we can knock out really fast before we move to our next presentation. It says, I'm hearing a lot about PFAS methods in drinking water. Is there an update to the wastewater method for PFAS 8327?
So the wastewater method, actually, when it comes out, it's going to come out as a 1600 series method. That's the latest. And there's two different wastewater methods. There's an 8327, which is basically a dilution of methanol and then analysis. Has some positives as a screening, has some issues with regard to the range of compounds that it purports to be able to analyze for. The other, what was its companion at one time, we were referring to it as 8328, is now taking a turn. It's going to be a 1600 series method. It's going to be isotope dilution. It's going to be for wastewater. It's going to be for soils, for tissues, for biosolids, for the kitchen, everything in the kitchen sink. It has gone through single lab validation. We're waiting for them to initiate the multi-lab validation. We're lucky enough to be one of the laboratories that's going to be participating in the multi-lab validation. So we're waiting and hopefully get that information anytime now. I do understand the proposed method has gone through, or the draft method has gone through 3 or 4, maybe 5 different revisions between the authors and EPA, and I think they're getting it fine-tuned to the point where they're going to hopefully soon put it out to we laboratories for the multi-lab validation, and then we'll be off to the races. At one point, I think they were talking to have all that finished up by the end of the year, but being as it's June, I'm sort of doubtful it's going to happen in that time frame, so hopefully early 2022.
Great, thank you so much, Charles. As a reminder, we are going to have a little extra time for Q&A at the end, so we hope that you'll be able to stick around after the close of the day as they continue to answer your questions. Next, we would like to welcome our last presenter, Dr. Chad Crane. Dr. Crane is the Microbiology Unit Supervisor at the Drinking Water and Radiation Laboratory Branch. He joined the laboratory in January 2016. Before joining CDPH, he worked as a senior research scientist in the biotechnology industry, where he conducted research on infection disease immunology and vaccine development. He received a PhD in cryobiology and a master's in environmental engineering from UC Davis and a Bachelor of Science in molecular biology from UC Santa Cruz. Chad runs the branch's certified water testing lab for microbial contaminants and is responsible for implementation of harmful algal bloom biotoxin methods for recreational water testing. In addition, he manages specialized research projects focused on environmental microbiology, such as the application of ddPCR for beach water control monitoring, validation of the receptor binding assays for monitoring PSP biotoxins, and development of environmental Legionella testing methods. His hobbies include swimming, surfing, and soccer. It's all yours, Dr. Crane.
Thank you, Jen. Can you hear me fine?
Yes, you sound great.
All right, wonderful. Well, thank you, everyone, and thank you for the introduction. I really appreciate the opportunity to present. The title of my talk is Application of ddPCR for the Detection of Enterococcus Species in Coastal Water Quality Monitoring. And this is a joint collaboration with California Department of Public Health as well as the County of San Diego. And this is a nice follow-up presentation to Susanna Thoreau, because this is the first formally approved molecular-based method for regulatory monitoring in the United States, and will be used as a pilot program in San Diego. Next slide, please. So just a little bit of background on the study. It included the entire San Diego coastline of the entire county, 51 sample locations, both wet weather and dry weather sampling, and over 3,000 samples collected. It was nearly a 2-year study with at least weekly testing and required quite a bit of statistical comparison of the methods. Enter-alert being the reference standard culture method against ddPCR, and qPCR method, the EPA 1609, used as a reference PCR-based method against the ddPCR, which is used as a training set. The size, the scope, and the expanse of this study required quite a bit of collaboration between the county and the state CDPH. Next slide, please. So here's just a list of the primary methods: Enter-alert, ddPCR, and TACMAN EPA 1609.1. Next slide, please. So the way this all started was there was legislation passed called SB 1395, which authorized qPCR to be used in place of culture-based methods for FIB monitoring and coastal water quality monitoring. Typical methods would take individual or take bacterial cells, culture them under regulatory methods from AB 411. These three methods would take anywhere from 24 to 96 hours, and then you would get your results. As an alternative, on the right side, you see this path going down, targeting specifically a genomic target, which could, of a highly conserved residue from the Enterococcus, which then could be amplified and then amplified and evaluated, and results could be generated within 4 to 6 hours as a single indicator, as opposed to 3, which was currently required. Next slide, please. So just this shows kind of a basic difference between the two, between qPCR and droplet digital. Traditional PCR is essentially takes the genomic target from the extracts in the bulk fluid and runs this enzymatic reactions in the bulk fluid, and it requires a certain threshold to meet quantitative analysis. Droplet digital as an alternative essentially take that bulk fluid sample and partitions them into thousands of droplets, which contain the same amount of reagents and varying concentrations of genomic target. And through this endpoint analysis, it lowers the threshold for analysis to a very, very low threshold, which is indicated on the right of this little graph. And the advantages of this is it's not sensitive to environmental inhibitors because they effectively get diluted out through the process, and there's no requirement for quantitative DNA standards, just basically control material. And through this endpoint PCR analysis, which is modeled to Poisson's distribution of the signal, it allows for an extremely lower limit of quantification for monitoring target signal. Next slide, please. The way we did this to evaluate this level of equivalency, we used the site-specific criteria issued by US EPA, which the primary method for modeling the level of equivalence is using the parameter called the index of agreement, which is illustrated in this equation, and going through a series of data steps using the IA calculation along with 30 measurable samples from both methods, and then meeting a certain threshold of 0.7 would indicate level of equivalence between methods. And as a secondary follow-up analysis, analytical or statistical parameter, we use the Pearson's correlation coefficient R, which is used as secondary to model equivalence. Next slide, please. So the study questions we had going into this was, there are 3 of them, and the first was, how well does the ddPCR 23S rDNA copy number correlate with Enter-alert MPN, which was more traditional and more commonly used for reporting, and when both tests have limits of quantification for both methods. And then how well do these correlate? How does the correlation patterns work? And is there a requirement of scaling? Distribution of the data, especially when implementing log transformation, which is required for the analysis. How well does the 2 statistical parameters use in evaluating their level of equivalence? And within that, once we establish the concept or the level of equivalence, is can the training subset of ddPCR and qPCR split samples that we used that were derived from this overall data set, can this training set be used as a representative data set to derive an intrinsic copy number equation to evaluate the molecular and culture-based readouts across a larger test set of 3,000 samples? And ultimately, The last question was, can 23SR DNA copy number be used as an alternative indicator for detection of actionable enteroalert levels as a fecal indicator bacteria? The California threshold value being 104 mpn per 100 ml in a single sample. Next slide, please. The way to do this, the way we had to do this is because it was such a big study and so many different samples across 51 sites. We had to aggregate them into 10 aggregate groupings, which basically combined sites based on their similar characteristics, which was to the left is a map of the entire county and the individual sample locations, and the right is a table of the aggregated groups in the gray and white. Next slide, please. So the way we had to look at this in terms of our database is that we had 361 samples, which were split samples taken from the larger data set that had qPCR and ddPCR samples, both in measurable levels. And within those 361 samples, there were 185 with enteroalert, paired enteroalert values. That we could use as a training set, a representative training set, which represented the larger test data set of 3,000 samples that were collected, but of those, only 1,993 samples had DNA copy numbers. We took that training set, put them through the modeling parameter of index of agreement and Pearson's correlation coefficient, and derived the intrinsic copy number equation, ICE, and applied that to the larger test data set, of which 1,086 samples had both DNA copy number and enteroalert MPN values that were measurable and could be used for comparison. Next slide, please. So the initial evaluation of the PCR-based methods was reassuring, in that, you know, the raw data collected from the samples showed a skewed distribution, but when log transformed, both methods showed a very nice normal distribution of samples, which is typical of environmental collected samples. The index of agreement that came out of that was 0.89, which was well above the threshold requirement for the EPA site-specific criteria. Next slide, please. And then also running linear regression analysis between these two, using the raw data or the log transform data, showed a very tight linearity between these samples, generating a Pearson's correlation coefficient of 8.7 with a very tight acceptable p-value of confidence. So that gave us confidence within our data and our approach to the way we're the PCR-based methods, that we were getting values that were reliable and representative of what was in the sample. Next slide, please. And looking at the limits of quantification, the lower limits of quantification between the two was also as expected. The ddPCR had a lower limit of quantification that was about 3.5 to 4 times lower than qPCR, based simply because of that threshold requirement is heavily reduced in the ddPCR as opposed to qPCR. So that was also confirmed. Next slide, please. So the next step was to really take the PCR, ddPCR, and evaluate it in the context of culture-based method. And culture and PCR methods measure the same bacterial organism but different target analytes. And analysis requires scaling to compare samples fairly. Now, measuring individual bacteria, as represented in the green cell, is basically 1-for-1. An MPN is representative of what total count of bacteria in the sample, but PCR readouts are typically much more elevated compared to culture-based method, because you have multiple target genes, multiple target gene copies of the same target, and that requires scaling. And essentially with the ICE equation, that you could apply that to the ddPCR-based readout, and that essentially attenuates the PCR readout to bring it closer to the culture-based method, so that the patterns not only match, but also the intensity of the readout, so they can be fairly compared to each other. Next slide, please. And the way this is applied is essentially it's derived, the ICE, or intrinsic copy number equation, is derived from regression analysis of the raw data. So remember, these are on totally different scales in terms of what the readout is, even though they follow the same pattern. So using the regression analysis of the raw data, the equation derived from the training subset of 185 non-transformed data points was used for measurable was used against measurable enter alert values. And it essentially creates the slope of a line at y equals mx plus b, which is illustrated in the next line below. When you implement your substitution for your x and y parameters, being DNA copy number and enter alert values, you get an MPN equivalent to a DNA copy number, and through a process of just simple rearrangement, you get the final equation, which is DNA copy number equals MPN minus 16.6 divided by 0.06183. And the scaling of the test data, using this equation allowed for scaling of the test data using the ICE to put them both in sort of a quantifiable range, although being very significantly different, ddPCR being much higher. But keep in mind that the limits of quantification for ddPCR is lower than even the range that we're testing here. So there are probably data points that we missed. Next slide, please. But when comparing the data of the molecular target to a culture-based target, you realize that, especially in the clean coastal waters of San Diego, you get a lot of significant skewing of the data. And this is just a natural consequence of collecting samples from real environmental sampling points. So the significant skewing of the enter alert data towards the lower signal readouts resulted in a biased mean comparator, so that the data was always being skewed to one side. And this has had to do with a lot of the low positive detects of enter alert values, and ddPCR being more representative, as illustrated in this normal distribution on the lower plot. It required reanalysis of the central tendency measurement of the index of agreement from mean to median, as well as evaluation of looking at non-transform data as well as transform data to evaluate what is actually impacting the behavior in the final analysis. Next slide, please. Looking at the overall table, this is a very busy slide, but the overall goal, the overall message behind this is really that we were able to achieve the index of agreement, looking at the index of the threshold for the index of agreement, using the different parameters within the model, either mean, median, or you're looking at the non-transformed data. Also, Pearson's R showed a very tight correlation and met the cutoff of 0.6 for non-transformed data. But what this really represented is that the log transformation was introducing a significant level of skewing of the enter alert data. So it really created a very difficult analysis for comparison, and there's literature to support that a better evaluation of this type of data set would be to using non-transformed data. That met the threshold in all cases, and so it demonstrated levels of equivalence across all the aggregate groupings that were used for the study. Next slide, please. So the next question, once we felt comfortable with the level of equivalence we were seeing between the two methods, we wanted to understand is how would beach management decisions be impacted when using a molecular-based method as opposed to a culture-based method, which is more commonly, which was traditionally used for AB411 monitoring in the coast of California. So we took the larger data set of that we had both where we had even the enter alert samples that were outside of the limit of quantification, and that totaled 1,993 samples that could be used for both DNA copy number and enter alert values to be used for beach management regulatory decisions. Next slide, please. From that, we set the ddPCR against the regulatory threshold of 104 MPN per 100 mLs for enter alert. The regulatory alert level for enter alert being 104 was directly compared to multiple ddPCR values using IC equation for all 1,993 points, and we conducted a ROC analysis, which was used to construct a percent agreement curve. And through that analysis, we identified the value of 1,413 DNA copiers being 90.4% equivalent to the value of 104 MPN. with a false negative and false positive rate of 6 and 3.7%, which is similar, if not better, than comparisons of culture-based methods between each other. Next slide, please. And just looking this in terms of applications, the EPA published their Rec Water Guide in 2003, publishing advised beach action values for Enterococcus using PCR or culture-based methods, putting the data from our study in side-by-side comparison. Our beach action value would come up as a 104 MPN per 100 mLs, which would be equivalent to the ddPCR of 1,413 copies per 100 ml, which could be used for regulatory enforcement. Next slide, please. So getting back to our original study questions, does the ddPCR 23S rDNA number correlate to enteral or MPN when both tests have results within the limit of quantification? The answer is yes. ICE scale ddPCR readouts align closely with enteral MPN for identifying FIB exceeding levels of Enterococcus in the study based on the IA and Pearson's correlation, so two statistical modeling parameters. Did the training subset from qPCR and ddPCR split samples serve as a representative data set to derive the intrinsic copy number equation? Was it consistent and reliable to scale molecular and culture-based readouts across the larger test data set? Well, yes, the answer was yes, the PCR methods were highly correlative. Both model parameters, IA and Pearson's, are exhibiting significant levels of equivalence for the PCR methods, and with enteralert following IC scaling. Outcomes suggest the training subset was representative of the larger test data set and appropriate for deriving the IC equation. And then the third question, was the DNA copy number a reliable alternative indicator for a detection of actionable enteral level, that being 104 MPN per 100 mLs? Yes, the value of 1413 DNA copy numbers correlated 90.4% of the time with enteralert MPN 104. The level of false positives and false negatives rate similar to culture-based methods, and suggested DNA copy number did serve as a reliable indicator for actionable FIB levels in the study and could be applied as a regulatory monitoring tool. Next slide, please. Presenting this data and this from the study, the EPA, they issued an approval for application implementation of this method in San Diego County as a pilot program to be used as the first in state as well as the United States application of a molecular-based method for regulatory monitoring. Next slide, please. And this is just an acknowledgement of the people involved in the study, with a special acknowledgement to Marvis Seifert, the data programmer, and Keith Seifert from San Diego County. Thank you.
Thank you so much, Chad. We are out of time for presentations right now, but we hope you enjoyed the presentations from today. Really fast, we'd like to welcome Anna Holder from the Office of Information Management and Analysis, or as we call them, OIMA, to tell us about a conference they're holding later this year that may be of interest to you. Anna, welcome to ELAP Con.
Hi, thanks for having me. Yeah, so if you can go to my first slide, I basically just want to give a quick shout out for the Water Data Science Symposium that's happening later this month. As you all know, high quality data from laboratories is critical for water quality management and public health decisions. And at the symposium, we like to highlight the great water data work that's being done throughout the state, and also prioritize having conversations around environmental justice, racial equity, and this year, tribal data sovereignty, and how, you know, data science and ecology and all of those topics kind of intersect. And we have a really great program that will be published later this week. The draft agenda is already on the website, and you can find information on that, that bit.ly link. And I also just posted something in the announcements. But to give you a little bit of a teaser, if you go to the next slide, we've got a couple, a really great 3-day sort of, well, 2.5-day event. On June 28th, we're going to have a native film screening on the film is called Paya, as well as a panel discussion about just water issues that tribes are experiencing and how we as a community can improve those situations. On June 29th and 30th, there will be traditional, symposium talks like you have been experiencing during the ELAP Con. And then on June 30th, we're partnering with the California Society of Freshwater Science to kind of hear from the emerging water and future water leaders in California and getting an idea of what they're working on. We're going to have a panel discussion on racial equity and to hear about the work that's being done throughout the state and kind of do an experiment on how we can make a path forward to how we can work together to kind of achieve some goals over the next year. And then there's also going to be a data workshop hosted by USGS and kind of exploring their Bay Delta data sandbox, and folks will be able to provide feedback and kind of investigate and all sorts of good stuff. So hopefully that's enough of a teaser for you to check out the website. And if you have questions, there's contact information on the website, and I will let you get back to Q&A. But thank you so much for letting me jump in and say hi to folks.
Great. Thank you so much. Some of you can join the event. That's all we have time for on our official agenda, and we have another great day of presentations in store for you tomorrow. So we'll see the rest of you back at 9 a.m. And just reminder that there's a unique link for each day, so make sure you check for the correct day when you join us. Tomorrow's theme is laboratory efficiency and performance improvement, and we'll have presentations about Lean Six Sigma, going paperless, quality management systems, lab automation, and more. So it's going to be another great day. We know some of you may need to go, but if you have time and have questions for our presenters, please feel free to stay and be involved and listen in. And also don't forget to join us on Slack. There the conversation has been going strong, and we have the PDF versions of the presentations available on Slack as well. So don't miss out on that. Presenters, thank you so much for sticking around. If you guys want to turn your cameras on, we'll let everybody see your smiling faces while you get to answer some questions. I think we'll just start at the beginning and move our way through. So the questions will probably be more or less in the order you guys presented, so that we can kind of try and keep the questions straight. So this one I think is for Jen Yu. The question is, oh, there it is. Are there any current studies on human health risks associated with 6-ppd-quinone?
Thanks. That's a good question. I haven't seen papers on the biological or toxicological side, but there's definitely a concern about human exposure risk. There's a very recent paper from Environmental Science and Technology Letter. They actually studied house dust and road dust, and they confirmed that 6-ppd-quinone is not only in the road dust, and also it's in the house dust. So there's a chance that people are exposed to that. And they also see like other PPDs, right? Like not 6-ppd, but other similar type of analogs in the house dust and road dust, suggesting that they might have, like a co-occurrence. That's the only thing we know, and there are definitely a need for addressing this question in the future. Thanks.
Great, thanks so much. This one's for Yegi. Could you explain why the recovery rate for the Giardia and crypto color seeds are what they are? Those recovery rate numbers seem lower than I would expect. And Yegi, I think you have to hit the *6 to unmute again.
Yes. So the complexity of the wastewater, we actually had a pretty hard time even recovering native cryptosporidium in the sample. And the reason we actually went to 8 slides were to make sure that we can cover as much as our spike as well as native sample as we could with the modification in the method. We had some instances where the percentage were higher than what I presented. However, averaging over 120 different samples at various times between laboratories, that is the average number we saw, more or less, in terms of recovery. And I think it has a lot to do with the complexity of wastewater.
Great. And then for Charles Wong, are there any special lab practices for testing microplastics, like clothing of lab staff who might bring lab microplastics into the lab room?
Yeah, contamination is a big issue because there's particulates everywhere, and and also many of those particulates are synthetic polymers, such as from synthetic clothing and other materials. So it is necessary to control for that, and also to kind of keep tabs on that with regards to knowing how much you've actually introduced in the process. That was evaluated within our study in terms of best practices for how to go about doing this, what's necessary and what is, desirable and what is probably, overkill. Again, that's kind of a general overview, but yes, absolutely.
Great, and we have another couple questions. They're all kind of close, so I'll just kind of rapid fire them at you, so maybe you can answer kind of one big answer. First, were there any colored natural fibers in the blanks? How do you ultimately decipher between the microplastics and natural materials? And then I'm wondering how many dyed natural fibers were in the distributed sample. Curious to know whether those could be distinguished using microscopy.
Okay, so blanks, there's what people reported on blanks depended on a whole bunch of things. First, it depended on the background contamination that we had when we generated the blind samples. We quantified that pretty well, and we've installed a positive pressure and HEPA filtration within the labs at SQUIRP. And a number of procedures. So our blanks are actually fairly clean. There's only basically like a couple of synthetic polymer particles present in each one. And then, of course, there's all the blanks, there's all the contamination that can happen after it leaves our facility and goes elsewhere. And, we obviously have no control over that. And that really varied from not much to an awful lot. With regards to things like telling them apart, if you want to confirm, you do need to do chemical confirmation either by spectroscopy or by mass spec techniques. That having been said, with some training and some experience, you can often tell a synthetic fiber from a natural fiber just by appearance. You won't be able to confirm it, but you can tell. With regards to dyed fibers, we actually didn't add dyed fibers specifically to our samples, at least not deliberately. Some managed to get through. So, for example, one very common dyed fiber that did get through are fibers that are blue from things like face masks, for obvious reasons. But that is an issue. The definition of microplastics that California's adopted for regulatory purposes is that fibers of more than 1% by weight of synthetic dye would fall under the definition. That's actually quite a bit of dye. So most things like your typical dyed cotton fibers would not have that much dye in it.
Great, thank you so much. And I think we have one more for you. It says it seems microplastic monitoring in drinking water is well on its way to implementation. Of the 5 methods and instruments you listed, which would be the best for environmental monitoring, not necessarily drinking water?
For environmental monitoring, yeah, and monitoring of things in the ambient environment is a somewhat different beast than drinking water, because the drinking water matrix is relatively clean. You're mostly just filtering and sieving. You're not having to get rid of all the other gunk, the natural particles and other materials that you do in a natural in a natural sample. We actually are working with 3 other matrices. So simulated surface water, dirty water with algae and sticks and other crud, as well as sediment and fish tissue. That data was actually technically due on Friday, this past Friday. It's basically slowly drifting in. So we're going to have the analogous set of data in a not very distant future to address those needs, and also to address the other piece of legislation towards developing a strategy for handling microplastics pollution in California coastal waters. So stay tuned on that one.
Great, thank you so much. Chad, I have quite a lineup of questions for you. Could you elaborate further on why some site categories didn't reach the higher IA criteria between EnteroAlert and ddPCR? The Tijuana samples tend to have higher enterococcus numbers, at least by EPA 1600 method, than other sites farther north.
Yeah, well, that's a good question. It's something that I think most coastal communities in California, when using this, will have to confront. You know, a lot within California waters, you have a lot of clean samples and a lot of low detects, and that really confounds your data and skews things significantly. You also have data that are heavily have a wide distribution, like Tijuana, where you have all or nothing coming out of it. So you have a lot of stuff depending on the flow of the river or discharges of treated sewer. You could have a really big flux, and so the data are not tightly bound or they're not normally distributed because they have such a wide distribution, and that's just something anybody would have to deal with. And so those are things that we had to consider when looking at this. And it is true, you do get a lot of non-specific targets from different methods that come up, especially from big point sources like Tijuana River. But in general, as we found when looking through all the data and modeling it through the statistical analysis, is that you have to really evaluate how that data is looking in terms of your distribution. That's really important. Culture-based methods have much more skewed distribution than molecular-based targets, and that's and there's a mathematical and scientific literature out there to support that. When you apply this nakedly as just your mean value, you're going to have a really huge mean bias reference parameter in your equation, and that's why the IA is so heavily affected by EnteroAlert. Whereas, as you saw with when comparing the molecular-based methods, they both had a very similar distribution in their data, and the IAs came up much more tightly. And when going through the literature and looking at non-transformed data, the transformation of the data is a requirement of the site-specific criteria. It says you must do this in order to put them on the same sort of playing field, but that actually makes it worse for heavily skewed data sets like what we saw with EnteroAlert. And we're not saying that everyone will see this within their sample package or their sample collection, but we did in this one. And I think many other counties, when trying to implement this, will see something very similar. And to know that there's a reason for that and how to get around it is important. So we think that our study will provide a nice platform or a base guideline for how other counties could do the same type of analysis. I hope to answer the question, but there's a lot going on within that.
Yeah, definitely another one for you. What does this mean for beach tourists? How fast can results be analyzed compared to the previous analysis?
Well, that's something for San Diego. I don't want to speak for them because they'll be the ones actually, doing the analysis and posting. But we kind of look at this as like early morning sampling, transport to the lab, and then by sort of afternoon at lunchtime, when you have peak visitation at the beaches, you'll be able to report whether it's safe to go in or not. And one of the things that Squirt always presented in a lot of their slides, which I thought was very clever, is that they would have a sign that would post beach water quality, and it would say, "We're posting the sign because you shouldn't. The water quality as of yesterday meant that you shouldn't have swam in it, so you could have a possible risk." So it's always delayed by an entire day. This would, at least in the rapid turnaround, would give you the data for that actual day of analysis as opposed to the day prior. So that, I think San Diego is looking at actually turning it around within the same day, early morning collection analysis, and then posting by midday sometime. How that will be done will be probably have to be refined as the implementation and practices actually go underway. But I think they have a good plan going forward.
Great. In the application of the ddPCR method, will each geographic area need to perform an equivalency study?
Yeah, well, that's something that EPA Region 9, I would defer to them, because they ultimately they would like to see this, intercalibration study across counties. And I know there are a lot of counties throughout California who are trying to do this. I don't think the counties would have to do a study as expansive and extensive as what we did. We really went over like as far as we could within the time period we had. But an abridged type of study comparing at least over a seasonal collection of samples, remembering that you need 30 measurable samples between both methods for direct comparison. I think it would be feasible. So that would at least give people sort of our study is kind of a little bit bigger. I think a little bit smaller intercalibration study over a beach season between counties would probably be sufficient. And ultimately consultation with SCWRP and EPA Region 9, since I think SCWRP is actually going to be providing some of the training in the future for this.
Great. I'll give you a second to catch your breath before you ask you a couple more questions, and we'll send the next one over to Chuck. Do you have any idea of how much money is being spent to test for PFAS in the United States using any of the methods?
I'm sorry, can you give me the question again? I got bleeped out when I tried to unmute there.
Yeah. Do you have any idea of how much money is being spent to test for PFAS in the United States using any of the methods?
Oh my goodness. Not really. Oh, there are estimates that put it at north of $100 million market, but I think actually if you would include all the DoD sites, it's probably even more than that. But no, I don't have a good handle on that. Sorry.
That's okay. We have a couple more questions for Chad. Will there be work done to compare ddPCR and EPA 1600?
I don't know. I think that remains to be seen. EPA 1609 or EPA 1600. Okay, yeah, sorry, I misunderstood. I thought you said 1609. I'm not sure, and I'm not sure if that's really necessary at this point. EPA 1600 has its own flaws in percent, variations, which are similar to EnterAlert. I don't think that would necessarily provide any new data. I think what is important is to understand that there's a big difference between molecular-based and culture-based methods, and particularly the way they're enforced for regulatory postings. That EPA did ask that question when we were providing our data for approval, and ultimately you find that there are more variations between culture methods themselves than what we found between ddPCR and EnterAlert. Whether or not since it is an approved method for beach water quality monitoring, it could be used as the primary reference comparator method for culture-based methods. But because of the ease of EnterAlert, and because it's used so widely across California, I don't see that there would be any new information, except that you would evaluate if there's any difference in percent agreement between the two methods. But that I don't know if there are any studies underway.
Okay, and then are there any differences in IA values when comparing wet weather samples and dry weather samples?
Generally, the data are better with wet weather because you get a much bigger signal coming out. Wet weather samples are kind of harder to get the reliable signal. That being said, dry weather samples typically have much more significant skewing from the culture-based data. PCR-based data tends to be much more reliable, and that was illustrated in the plots, the histogram plots, where you see a nice normal distribution of the PCR data and a significant skewing of the EnterAlert data.
Great, and I think actually I'm going to throw this one to internally to Chris Hand. Well, first of all, he says great presentation on PCR-based methods for Enterococcus, and congrats on the EPA approval. What is the path forward for this method as far as ELAP certification is concerned?
Yeah, and I was going to answer that just to give a general idea of how methods move through ELAP's accreditation process here. So all of our method offerings start with a request from one of our regulatory agencies. And in this case, the Department of Public Health, who implements the beach monitoring requirements, sent us a letter just at the end of May. And so adding it at the end of May, we are working closely with Chad and folks in San Diego, as it is going to be limited to only San Diego County at this time, mostly because the study and approval that was granted from US EPA was limited in scope just to San Diego County. So at this time, it'll only be for San Diego County, and we are working on adding it to our list. Of course, we're going to have to learn the method process itself, get some training for our assessors, get some training for the third-party assessment agencies that'll be assessing the performance and things like that. So it does take a little bit of time.
Awesome. Well, guys, thank you so much for being here. We have cleared out the chat box of all the questions. We want to thank all of our presenters for being here. We are so glad and so honored that you took some time out of your busy schedules to be here for part of us. And of course, as soon as I said that, another question pops up. So what are the sample preservation requirements for inter-alert samples? Oh, you're on mute, Chad.
Inter-alert samples have to be measured within 6 hours because they are environmental samples. So that's one of the, why that we had to break up the study between San Diego and CDPH. The DNA samples can actually be frozen. So that's one of the advantages of those as well, of doing that method.
Awesome. Thank you so much. Well, like I was saying, we really appreciate all of you being here and part of the ELAP conference and the time that you took out of your days to be here for that. And we would like to welcome all of our attendees back tomorrow morning. Look for the link that's dedicated to day 3, June 3rd. And we will see you then. And don't forget, we are busy chatting away on our Slack channel. So we'd love to see you there.